In this section, we're going to look at constructing proofs by induction, a technique used to prove certain kinds of theorems.
In mathematics, we are often tasked with proving something is true. Now, depending on what we're trying to prove, it may be a simple matter of concentrating on a single object. I'm trying to prove that something is true for this function. Oh, well then I just focus on this function. However, there are times where you need to prove that things are true for all functions. Some things that are true for all numbers, some things that are true for all cases, in which case you have often an infinite number of things to do. For example, let's say we were trying to prove something like 1 squared plus 2 squared plus 3 squared plus ... all the way up to n squared. That's equal to n times n plus 1 times 2n plus 1 divided by 6. Let's say we were trying to prove that that were true. Okay, how would I do that? Well, one thought is I could actually just plug in a number. I could say, well, what happens when I plug these in? In fact, let me do that. Let me just take, let's say n is equal to 4. Okay, so I would have 1 squared plus 2 squared plus 3 squared plus 4 squared. And there we go. I stopped with n equal to 4. And that's going to equal to 4 times 4 plus 1 times 2 times 4 plus 1 over 6. All right, well, let's see. 2 times 4 is 8. 8 plus 1 is 9. That's 5, and that's 4. Okay, so 4 times 5 times 9 over 6. 4 times 5 is 20. 20 times 9 is 180. And 180 divided by 6 is 30. Over here, let's see what happens on this side. Well, let's see. 4 squared is 16. 3 squared is 9. So 16 plus 9 is 25. 2 squared is 4. So 25 plus 4 is 29. Plus 1 more is 30. So yes, that works. So you might think, okay, great, we proved it. Well, no. We only proved it for n is equal to 4. What happens if n is equal to 5? Oh, well, let me plug in 5 and see what happens. Okay, great. And that'll take you another minute or so. You'll get that. But what about when n is equal to 6, or 7, or 8, or 9, or 100, or 1,000,000? You couldn't possibly test all of them because there's an infinite number of these. Here, this is true for all values of n. How could you possibly prove that? If we were trying to say this is equal to this when n is equal to 4, you could test that. You could say, okay, let me plug in 4 and see what I get. If the statement was this is true for all single-valued values of n, 1, 2, 3, 4, 5, 6, 7, 8, or 9, it might take me a few minutes, but I could do that. I could plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, and test all of those. And I could confirm that. But when the statement is something like it's true for every number, that is prohibitively long. You cannot prove this by testing individual cases because you would literally never finish. There are an infinite number of cases. So the proof of this statement would not be doable by just testing individual cases. What we need to do here is use a more advanced proving technique, a more advanced proof technique, which is called mathematical induction. Mathematical induction is basically 2 steps. Now, those 2 steps can be a little cumbersome, they can be a little big, a little long, but they are basically just 2 steps. So let's summarize that here. Mathematical induction. Okay. Let's begin with a statement. Let S sub n be a statement to be proved, to be proven, yes, there we go, to be proven for all integers n. Note here, these have to be integers. We can't use, well, actually, it shouldn't even be integers. They should be counting numbers. So we don't even include negatives here. So let me correct that. We don't even have integers necessarily. We have specifically counting numbers, starting from 1, 2, 3, 4, on and so forth, for all counting numbers. Okay. If S sub 1 is true, so you've proven that it's true for the very first number, and the truth of S sub k implies the truth of S sub k plus 1 for every counting number k then our statement is proven by induction. Our statement S sub n is true. It's been proven. So that's basically what mathematical induction is. It states that, all right, you want to prove something is true for every number. First of all, you have to prove that it's true for the first number. Okay. Then you have to prove that it being true for a number means that it's true for the next number. So if it's true for the first case, then that means it's true for the second case. But by being true for the second case, that implies it's true for the third case. And if it's true for the third case, that implies it's true for the fourth case, and that implies the fifth case, and the sixth case, and so forth. So it automatically, by proving the first case, and by proving that one case proves the next one, it sets off a chain reaction. So here, your S sub 1, you need to prove that that one's true. And then, you're going to prove that S sub 1 leads to the truth of S sub 2. Oh, but that would lead to S sub 3, and that would lead to S sub 4, and that would lead to S sub 5, and because that will always be true for every number, that will continue on forever. So by proving that very first one, it will automatically prove all of the remaining ones. That's called mathematical induction. Now here, that's a little bit hard to understand by just reading this statement, so let's look at some examples. Here, let's start off with this very first one. So example, I'm going to rewrite it down here. Let's prove the truth of the following statement. 1 squared plus 2 squared plus ... plus n squared is equal to n times n plus 1 times 2n plus 1 over 6. Okay? Here, we're not going to solve anything. We already know what it's supposed to equal to, at least what we think it's supposed to equal to. What we need to do is we need to prove that this is equal to this for all n. So obviously you can't do it by plugging in n is equal to 4 and saying, okay, that works, and then n equals 5 and that works, because you would literally never finish. So instead what we're going to do is we're going to use mathematical induction. All right, so the first step of mathematical induction is proving the first case. Step 1, prove the first case. Which up here you see is labeled as S sub 1. Okay. Proving the first case is always very, very simple. All you need to do is plug in 1. Right? So right here, if you're saying, all right, I want the first case, that means you took 1 squared and that's it. You just stopped right there. Okay? So the first case is you start at 1 squared and you keep going until you get to 1 squared. Or in other words, that's it. That's all you did. You just did that first one. So 1 squared is equal to, and then on the other side, anywhere there's an n, you're going to plug in the number 1. Okay, well, let's see what both sides of this equation are. 1 squared is equal to 1. And on this other side, well, let's see. 2 times 1 is 2, plus 1 is 3. Okay? 1 plus 1 is 2, and that's just the number 1. So 1 times 2 times 3 over 6. 1 times 2 times 3 is 6, divided by 6 is 1. Okay, so that is true. We have proven S1, we've proven the first case, and we've done that simply by plugging in the number 1. All right, so here n was equal to 1, and we just took the first case. Now, the next step is going to be to show that, so step 2, and this is the one where the bulk of the work comes in, we're going to show that if S sub k is true, that implies that S sub k plus 1 is true. Okay. So let's begin by saying, okay, well, what is S sub k? Okay, well, S sub k is equal to the sum of the first k terms. So that's 1 squared plus 2 squared plus dot, 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 all the way up to k squared. And let's say it's true up to this number. Let's say it's true for the first number, for the first two numbers. In fact, over here we proved that all the way up to the fourth number, right? Okay, that's fine. You can always prove the first 2 or 3 or 4 manually, whatever. Here, we're not even going to bother doing that. We're just going to say, okay, let's just say it's true up to some number. Okay, well then what must be true? Well, if I replace this n with a k, then I'm replacing these n's with k's. So that would be k times k plus 1 times 2k plus 1 over 6. Okay, so right here I'm starting with the S sub k case. And I'm going to say, okay, let's say we know that's true. Okay, then let's see what happens if we find S sub k plus 1. All right, well, let's do that. I already have S sub k is equal to this thing. Okay, so what is S sub k plus 1? Well, that's what happens when you add the next term. You're going to add k plus 1 squared. Okay, and in fact, let me do that in a different color. Here, all of this stuff was what I already had. And now I'm going to add the extra term, k plus 1 squared. Okay, well, that's an equation. If I add something to one side, I have to add the same thing to the other side. Okay, so that's going to be k times k plus 1 times 2k plus 1 over 6. And, again, that in blue is that in blue. That's equal to this stuff in blue. But now on this side, I've added k plus 1 squared. I've added the next term. So whatever I do to one side of my equal sign, I have to do on the other side. I'm going to add k plus 1 squared here as well. So now let's rewrite this. Right? Nothing complicated, just some algebra. We're simply going to add these two things together. Okay, so here this is my S sub k plus 1. Okay, well, let's see what happens. I'm going to expand this and I'm going to simplify. All right, let's begin by adding these together. Let's see here. I'm going to give these a common denominator. So I'm going to switch over to another page now. And let me just rewrite the last line over here. I had S sub k plus 1 is equal to 1 squared plus 2 squared plus dot, 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 plus k squared is equal to k over k plus 1 times 2k plus 1 over 6. And what I did was I said, okay, that was my S sub k. That was the one that I can assume. I'm assuming that's true. And now, to find S sub k plus 1, I'm going to add the very next term. I'm going to add k plus 1 squared. And whatever I do to one side, well, I do to the other side. Like that. Okay. So now here what I'm going to do is I'm going to add these two together. The way I'm going to do that is I'm going to, well, let's see. I'm going to give these a common denominator, first of all. So let me go ahead and write this one as being over 6. So that's equal to, I'm just bringing this down here. It's going to be k over k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. And I'm going to go ahead and multiply the top and bottom by 6 so that they have a common denominator. And that way I'll be able to add them. Okay, so let's see. Now that I can add them, they have a common denominator of 6. And I have k times k plus 1 times 2k plus 1 plus 6 times k plus 1. Okay. Notice one thing here, that they both have a k plus 1 as a common factor. So I can factor that out. So I can write this as k plus 1 times, now let's see what happens when I factor out the k plus 1. I'm left with a k and a 2k plus 1. And over here, I factored out one of these k plus 1s, which leaves me a 6 times the other k plus 1. And again, all of that is over 6. Okay, I can simplify this numerator. Notice I can just distribute and combine like terms. So here, the k plus 1 is on the outside. Here I have 2k times k, that's 2k squared. K times 1 is k. 6 times k, that's 6k. And 6 times 1 is 6. Like that. Notice those are like terms. I can combine those. So that'll be k plus 1 times 2k squared plus 7k plus 6 over 6. I can factor that though, can't I? That will give me factoring these will give me 2k plus 3 times k plus 2. I think that works. That's 2k squared. That's 4k plus 3k, that's 7k, and then 3 times 2 is 6. And all of that is over 6. Okay, cool. So now what? Well, now notice that this can be rewritten this way. First of all, I'm going to reorder some stuff here. First, I'm going to write k plus 1 times k plus 2 times 2k plus 3 over 6. Now, nothing's happened. All I've done is I've changed some order here. I've changed the order of the numerators. It's on multiplication, so it doesn't matter what order it's written in. Notice that this is the same as saying the following. This is, and I'm going to write this in red here. This is k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. That is exactly the same as what this side says. Right? That's a k plus 1. K plus 1 plus another one, that's k plus 2. And then here, 2 times k is 2k. 2 times 2 is 2, plus 1 more is 3. So those all say the same thing. Okay, so why did you write it that way? Because this is the same form that you had up here. Notice that if you have s sub k, that's equal to k times k plus 1 times 2k plus 1. But now if I have s sub k plus 1, well, notice that follows the same pattern. But instead of a k, that's a k plus 1. And instead of a k, that's a k plus 1. And instead of a k, that's a k plus 1. So what that means is that our formula was true not only for s sub k, but also for s sub k plus 1. So if the formula is true for s sub k, then here we show that if you change the k to k plus 1, it's still true. Because look, you can replace those k's with k plus 1s, and the formula still works. So if the formula is true for s sub k, this shows it's true for s sub k plus 1. Oh, okay. So if you know it's true for one case, then it's got to be true for the next case. Oh, but we already proved this is true for S sub 1. That's what we did at the very beginning, right? That was our very first thing that we did. We showed that it was true for S sub 1. So if it's true for S sub k, it's true for the next one, S sub k plus 1. But we already showed that it's true for S sub 1, which means automatically it's got to be true for S sub 2. Oh, but now we know it's true for S sub 2, so automatically that means it's got to be true for S sub 3. Oh, but now it's true for S sub 3, which means automatically it's true for S sub 4, which automatically means it's true for S sub 5, which means it's true for S sub 6, and on forever. So, therefore, 1 squared plus 2 squared plus ... all the way up to n squared is equal to n times n plus 1 times 2n plus 1 over 6 for all numbers. Because now we know it's true for 1, and we proved it's true for 1, which suggests it's true for 2, which suggests it's true for 3, for 4, for 5, for 6, and forever. So this is true for all n. And that would conclude your proof. That's how induction works. You first show that it's true for the first case. Then you start off with the k step. You just plug in k for everything. And then add your next term to both sides, whatever that next term is. Once you've added it to both sides, you're going to simplify. And once you simplify, it should give you the same formula, but instead of having a k in place, it'll have a k plus 1 in place. Now, sometimes that's a little hard to see. Here you might wonder, well, wait a minute. Okay, I see that you got a common denominator, and I see that you put things together and you factored. But once you got here, how did you know that is what you were supposed to do next? Like, okay, I get that you can add them with a common denominator, and I get that you can simplify. But how did you know factoring was the next thing to do? Is it always going to be the next thing to do? So you can kind of work, you can kind of work with what you know should happen, or at least what you suspect should happen. I kind of knew what formula I was going to get. So here, there is, a first step, there's a second step. There's going to be what I'm going to call step 1.5. You don't usually find this in any of your textbooks, and it's not officially a step that you use in mathematical induction, but here I'm going to say, okay, I'm going to call this step 1.5. Find what the result should look like for S sub k plus 1 if everything works out. So our formula was, the one we're trying to prove is this one. If you're adding everything up to the nth term, then you're going to have an n there, an n there, and an n there. So let's say I went all the way up to k plus 1, because that's what my step 1.5 is going to be. I want to find out what happens to my k plus first step. Okay, well then that would be 1 squared plus 2 squared plus all the way up to k plus 1 squared. That's equal to, I'm going to replace that n with a k plus 1. I'm going to replace that in with a k plus 1, and notice that that's already got a plus 1 there, so k plus 1 plus another one, that'll be k plus 2. And then here, that's going to be a k plus 1 as well. If you double k plus 1, that's 2k plus 2, plus 1 more, that'll be 2k plus 3. So here what I've done is I've said, okay, if everything works out, here's what I should get at the end. I should get that if I plug in a k plus 1 into my formula, I get this as my result of my formula. K plus 1 times k plus 2 over 2k plus 3 over 6. So now that I kind of have a target, now I know what to look for. So here, okay, that definitely doesn't look like what I want. So that means I need to keep simplifying. Okay, let me combine them, because over here I have one fraction, not two. So let me combine like terms with a common denominator. Oh, but everything's over here factored. Here this isn't factored, there's a big plus sign right in the middle. Okay, so let me combine stuff so then I can factor. Oh, okay, but now that I factored, hey, that looks exactly like what I wanted. So by doing this, this sort of gives you a target. It tells you, okay, in the end, here's what you should be looking for. If everything works out, if the statement is true, then this is what you should get. Notice that if. Remember, whenever you're trying to prove something, sometimes it won't be true. But if what you're trying to prove is true, this is what you should get. So keep that in mind. If everything works out, this is what you should get. So start from here and do whatever you can to try to make it look like this. If in the end it's not possible, well, then that means your statement probably wasn't true then. So let's take a look at another example of how to do this, starting from the top. Let's prove the following statement. So another example, we're going to go ahead and prove the truth about the following statement. Oh, let's see. Let's try. Here, let's try this one. The sum of 3 plus 6 plus 9 plus dot 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 plus 3n, that's going to equal to 3 times n plus 1 over 2. And we're going to prove that's true for every value of n, for all n, where, again, n are counting numbers. Okay, so here we go. Start off by proving the first step. Step 1. Let's prove S1. And that one's always really simple. You take the first term over here, and that's going to equal to what you get when you plug in 1 over here. And that should be true. If it's not, well, then right away our formula is wrong, right? So here that's going to be 3 times 1 times 1 plus 1 over 2. Okay, well, 1 plus 1 is 2. 2 times 1 is still 2. Times 3 is 6. And 6 divided by 2 is definitely 3. So yes, we have proven case number 1, S1. Okay. Now, here I'm going to say step 1.5. This is not technically a formal step of this process, but it is a very useful step because it helps to give an idea as to what you're eventually going to get. So here, step 1.5 is what should my result look like if this statement is true, the one that you're trying to prove. Okay. All right, well, my statement should involve, instead of an n, I should end up with a k plus 1. Because in the second step, I'm going to say, okay, if I know k is true, let's see if k plus 1 is true. Okay, so what does it look like for k plus 1 to be true? All right, well, that'll be 3 plus 6 plus 9 plus dot, dot, dot. And then here, instead of an n, now have a k plus 1. Okay, well, that means this n and this n will be k plus 1s as well. So that's 3 times n. That becomes 3 times k plus 1. And then over here, that n becomes a k plus 1. But I have another 1. So that'll be k plus 2. And then that's a constant. It's not changed. If you make changes to your variables, the constants aren't going to change. So the 3 and the 2 stay the way they are. So here, this is giving you something to shoot for. By the time you're done, if you can make your statement look like this, then yes, your statement is true. Right? Otherwise, it wouldn't be true. All right, so now let's take step number 2. And that is, okay, assuming the kth step, assuming case S sub k, show this implies case S sub k plus 1. All right, so let's start off with our kth step. And the kth step is simple enough. You take your original formula and replace your n's with k's. The only reason we replace them with anything at all is so that we don't have 2 copies of the same formula running around. We're using k for our proof, and then n is the final result. It's just the semantics. It's just to keep things from getting mixed up. So here that's going to be 3 plus 6 plus 9 plus ... all the way till you get to 3k. And that's going to equal to 3 times k plus 1 over 2. Okay? So that's the kth step. And here we're just assuming that's true. But now, if that's true, let's show that that implies that s sub k plus 1 is true. Okay, so the way you're going to do that is you're going to say, well, that's the kth step. The next step would be me adding one more of these. So instead of adding 3k, I would add 3 times k plus 1. Okay, well, whatever I do to one side, I do to the other side. Add 3 times k plus 1. Okay, so now I'm aiming to turn this into this. Now, we don't know if we can do that. If we can't do it, then that means that this isn't true. But that's what we're aiming for. So notice the thing we're aiming for is a single fraction, not the sum of two expressions. So my first step is probably I want to merge those two together. Okay, so that's going to be 3k times k plus 1 over 2 plus 3 times k plus 1. To put these two together, I need a common denominator. So I'm going to multiply the top and bottom by 2. All right, well, that's going to give me 3k times k plus 1. And now that they have a common denominator, I can merge all those together with a single denominator of 2. So 3k times k plus 1 is here, plus, and now notice over here I have 3 times 2, that's going to be 6 times k plus 1. Looks like that. Okay, so they have a common denominator. There we go. These two are here, and this is right over here. Don't forget your plus sign. Okay, well, that's closer to what I want. It's a single fraction now, but it's supposed to be all factored out in the numerator. That's not what I have here. So let me try to factor this. Notice right here I have a common factor. In fact, I have two common factors. They both have a 3 in common and a k plus 1. So let me factor that out. 3 times k plus 1. All right, well, if I factor out 3 times k plus 1, what am I left with? Well, if I factor out the 3 and the k plus 1 here, I'm left with just my k. Okay, plus, if I factor out the 3 and the k plus 1 here, the k plus 1 is divided away. 6 divided by 3 is 2. And all of that has a common denominator of 2. Oh, but look, that's what I was aiming for. 3 times k plus 1 times k plus 2 over 2. Oh, okay, so there we go. Here, I'm going to rewrite this ever so slightly as 3 times, and here I'm going to color code it. You don't have to color code anything, but that's just, as the instructor, I like to color code stuff to try to make them stand out. Here you can write that as 3 times k plus 1 times k plus 1 plus 1 over 2. Which you will now notice is exactly the formula that we had before with k plus 1 plugged in everywhere. So if you have the k plus first step where you've added together all the terms starting from the first one up to the k plus first one, you're going to end up with this formula with k plus 1s plugged in wherever there's an n. 3 times k plus 1 times k plus 1 plus 1. 3 times k plus 1 times k plus 1 plus 1 all over 2. So in other words, the formula applies if it applied to the kth step, then by adding the next term, you can confirm that the same formula applies to the k plus first step. So incidentally, this step right here is called the inductive step. In most textbooks, it'll be referred to as the inductive step. And once you have shown that the S sub k case leads to the k plus first case, that is your result. So, therefore, our statement is true. 3 plus 6 plus 9 plus all the way up to 3n added together gives you 3n times n plus 1 over 2 for all integers, so for all counting numbers n. where again the counting numbers are 1, 2, 3, 4, 5, and so forth. Note here that there is no single final answer. There is no one thing where I can say, okay, here's the answer. I'm circling this, or I'm circling this. The entire process is the answer. Here, it's not a single result that you're getting. Rather, it's the proof of a formula. So every step is part of your proof. So if I was going to circle my answer, I would just put a big circle around the entire page. Every step here is required. These do take a bit of getting used to, and you certainly have to try a few of them to get the hang of it. So go ahead and give this a try. You're going to prove the following statement using induction. All right, so go ahead and give this one a try. Prove that the sum 3 plus 7 plus 11 plus ... all the way up to 4n minus 1. Prove that that is equal to n times 2n plus 1 for all counting numbers n. Okay. Go ahead and pause the video and give yourself the time you need. And once you are done, you can unpause and we will go through and confirm this together. All right, so here we go. Your first step, you're going to prove S sub 1. Okay. That one's a nice case, because S sub 1 is just take the first term from the left, so that's the number 3. And then on the right, you're going to plug in the number 1 and see what happens. That's going to be 1 times 2 times 1 plus 1. Here, 2 times 1 is 2, plus 1 is 3. And that's getting multiplied by 1, which, yes, that is absolutely true. So here we have proven S sub 1, because taking the first term is what you get when you plug in the number 1 to the right-hand side. Now, your step 1.5 is technically not necessary, but it is often very useful to see what your answer should look like, assuming that everything works out correctly and this is a true statement. Now, mind you, if this is not a true statement, if you were trying to prove it and it turns out not to be true, well, then you won't get this result. So here, that's what I'm saying, if it works out. So here we go. The k plus first step, what should S sub k plus 1 look like if the statement is true? Okay. All right, well, that means you're going to start adding all of these numbers up. So you're going to start from 3 plus 7 plus 11 plus ... plus and then you're going to go up to until you get to k plus 1. So this n will be replaced by a k plus 1. So that'll be 4 times k plus 1 minus 1. 4 times k plus 1 minus 1. And that should equal to, this n will be replaced by a k minus 1. A k plus 1. And this n will also be replaced by a k plus 1. So 2 times k plus 1 plus 1. And here I'll even simplify that just a little bit. I can write that as k plus 1 times 2k plus 2 plus 1 more. Okay, so that's 2k plus 3. Okay? So if everything works out, that's what you're hunting for. All right, so let's see if we can find that. Step 2. Let's see what we get. So step number 2 is if, so show that S sub k implies S sub k plus 1. All right, so let's give that a try. Let's begin with S sub k. That's this formula. We're just going to replace the n's with the k's to keep it separate from the final result. So here that's going to be 3 plus 7 plus 11 plus ... plus, and we're just going to replace that n with a k. So 4k minus 1 is equal to And then on this side, we'll replace those ends with k's. So it'll be k times 2k plus 1. All right, but if that's the s sub k, what would s sub k plus 1 look like? Well, I would have to add the next term right here. Okay, well, the next term will be what I get when I have, instead of a k right there, I have a k plus 1. So let me add 4 times, instead of having a k there, it'll be k plus 1 minus 1. Okay, that's the s sub k in blue. By adding this one more term, that's the next one, s sub k plus 1. Oh, but what if I do to one side, I got to do on the other side. So over here, let me add 4 times k plus 1 minus 1. Okay. All right, so now I notice over here that in my step 1.5, I noted that my final result, I'm hunting for a factorization. Okay, well, I don't have any factorizations here. So let me see if I can't simplify that. That's equal to, let me begin by just distributing and combining terms. All right, so here that's going to be k times 2k, that's 2k squared, and k times 1 is k. Plus, now I'm doing this part in red, 4 times k is 4k, 4 times 1 is 4, and then outside of the parentheses I have that minus 1, so that's just minus 1 on its own. I notice I have some like terms that I can combine, so that's going to be 2k squared. I have a 4k plus 1 more k is 5k, and then 4 minus 1, well, that'll just give me 3. Now this can be factored. It's quadratic, so it'll factor as 2 linear factors. This will factor as, let's see, 2k plus 3 and k plus 1. Because after all, 2k times k is 2k squared. That'll give me 2k, and that'll give me 3k, which is 5k. And then 1 times 3 is 3. Oh, but that's what I was hunting for. I was looking for my k plus 1 times 2k plus 3. So here that's, let me rewrite it back in the correct order. K plus 1 times 2k plus 3, which is, in fact, k plus 1 times 2 times k plus 1 plus 1, which is exactly what it would look like if you took your formula that you were trying to prove and plugged in a k plus 1 there and a k plus 1 right there. Ah, okay, so then that is correct. By starting by assuming my s sub k, which I did in blue, that was my assumption. By adding the next term to get me from sk to sk plus 1, I can rearrange it to still give me the formula. So sk implies sk plus 1. Oh, but we proved that it's true for the first step. We proved that it's true for S1. So then that implies it's true for S2. Oh, but then that in turn implies it's true for S3, which in turn implies that it's true for S4 and S5 and S6 and so forth and so on. Thus, by mathematical induction, you have that 3 plus 7 plus 11 plus ... plus 4n minus 1 is equal to n times 2n plus 1. And so this is a true statement. This is an actual valid formula right here. So that is our result. Note that I don't have a final answer that can be summed up nicely. If you were saying, okay, so what's your final answer? I would put a big circle around every single thing that I've written, because every part of this is the proof. And that brings us to our results, which does conclude our proof. All right, so that is it for this section as well as for this topic. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.